Today we are going to study the second part of the dual nature of radiation and matter, that is Einstein's photoelectric equation. Now, according to Planck's quantum theory, the energy of electromagnetic wave, they are not constantly distributed over the wavefront of wave. Actually, they are in the form of discrete packets of energy and they are called photons. Now, how much energy are they carrying? They are actually carrying energy equals to h nu, where h is the Planck's constant and nu is the frequency. Now, when this energy h nu strikes the metallic surface, this is a metallic surface, when it strikes here, the electrons in the metallic surface absorbs this energy and it uses in two ways. First, they absorb it and they try to overcome the barrier present in the metal and cross the metal. They want to come out of the metal and that is called work function phi naught equal to h nu naught. So the first one it uses as work function and the second one it gives some velocity to the photoelectrons emitted over there. So that velocity is used as kinetic energy of the photoelectron. See, half mv square. Kinetic energy of the photoelectron. So I can write here kinetic energy max equal to half mv square. So again I am repeating, this energy h nu which is coming from here, from the radiation, E equals to h nu, this is striking the metallic surface and it is being used in two manners. First as the work function to overcome the barrier and cross the metallic surface, means it is coming out of the metallic surface, and second to impart the kinetic energy to the photoelectron. So how to write this now? We can write in this manner, h nu equals to h nu naught plus half mv square. So this can also be written as half mv square max equal to h nu minus h nu naught, or kinetic energy max equal to h nu minus work function. Now this particular equation, kinetic energy equals to h nu minus phi, that is your work function, this is known as Einstein's photoelectric equation. This can further also be solved as, you can also write it in this manner, h nu minus h nu naught. You can take h as common, nu minus nu naught. It can also be written in this way. Okay? You can take the screenshot. Now, relation between stopping potential V0 and threshold frequency nu naught. Just now we have seen from Einstein photoelectric equation that K max equal to h nu minus nu naught. So K max equal to h nu minus h nu naught. Now what is this nu and what is this nu naught? Nu is equal to C upon lambda and nu naught is equal to C upon lambda naught. What is this lambda? Lambda is the wavelength of incident radiation and lambda naught is the threshold wavelength. And c is of course the velocity of light in vacuum, which is a constant quantity. And we also know that K max is equal to E V naught. So let us put this value and we get here E V naught equals to, see here I am putting the values over here. So H I can take common also here, C upon lambda minus C upon lambda naught. C again I can take it outside, HC 1 upon lambda minus 1 upon lambda naught. So finally what I am getting? Very easy one. E V naught, I will write here, E V naught equal to HC 1 upon lambda minus 1 upon lambda naught. So this is the relation between stopping potential and threshold frequency. Now we will be seeing the graphs. We will be studying about the graphs. Now the graphs related to photoelectric effect from Einstein's photoelectric equation. So the first graph we will plot of frequency versus stopping potential. On the y-axis we take stopping potential and on the x-axis frequency. We have seen from Einstein's photoelectric equation that kinetic energy max is equal to h nu minus phi naught, that is the work function. And h nu is the energy of the photon which was striking the metallic surface. So kinetic energy is also equal to E V naught. V naught is the stopping potential. So we can write over here E V naught is equal to h nu minus phi naught, or V naught is equal to h nu upon E minus phi naught upon E. So it is very much clear here that V naught, that is stopping potential, will be directly proportional to the frequency. So if we plot a graph, we will be getting a straight line over here. And the slope is also always equal to tan theta. So here tan theta will be equal to h upon E. And see, this is a straight line and we can see it very clear that this curve is independent of the nature of the material. Okay, so take the screenshot. Now, the graph of frequency versus maximum kinetic energy. We take in y-axis maximum kinetic energy and on the x-axis frequency. And from the equation which we discussed earlier, K max is equal to h nu minus phi naught, where phi naught is your work function and h nu is the energy of the photon. So we can see here that again K max is directly proportional to your frequency, because all these phi naught is a constant, h is your Planck's constant. So the nature of the graph is again a straight line and tan theta is equal to your h. H is the Planck's constant. Take a screenshot of this. Now the third graph, frequency versus photoelectric current graph. Now we can see here that on the y-axis we have taken photoelectric current and on the x-axis frequency. And which type of graph we are getting here? See, we are getting here a straight line here which is parallel to the frequency. What does it mean? Even on increasing the frequency, photoelectric current remains constant. So I is independent of frequency. Current does not change on increasing the frequency till intensity remains constant, provided we are not changing the intensity. Take the screenshot. Now the fourth one, intensity versus stopping potential graph. Here we see that on the y-axis we have taken stopping potential and on x-axis intensity. So now as the intensity is increasing, the stopping potential does not change. What does it mean? That stopping potential is independent of intensity. So you take the screenshot of this also. Now the last one, photoelectric current and time lag graph. On the x-axis we take time and the y-axis we take photoelectric current. So we can see that 10 to the power of minus 9 second. This is your time lag, and you can see the nature of the graph till here. After 10 to the power of minus 9 second, the flow becomes steady. You take the screenshot of here this also. So now we have discussed all the graphs, 5 type of graphs, and we have also discussed your kinetic photoelectric equation. So this concept must be clear to you all. Okay children, thank you.